Today we're going to talk about industrial applications of IoT implementation. We're going to do an overview of what IoT is and discuss two cases. So IoT is an abbreviation for Internet of Things. It's basically a system of devices with sensors of some sort that are used to collect massive amounts of data, and then you can take this data and do useful things with it. It's a conjunction of data acquisition, sensor networks, and internet technology. So we see a rise in IoT devices because of the relative cheapness of and quality of newer sensors and computers. Some good examples of that are the Arduino, Raspberry Pi, other microcontrollers with with lots of computing power and a small size, small power consumption, and the ability to take in information from different sensors. There's been a rapid increase in the value of data as a commodity as its usefulness has become more obvious and our ability to collect it has become a lot easier, along with newer, more intuitive tools. A good example of IoT that everybody should understand is a home security system or smart home of some sort, where all the information from the home is uploaded to a local network or a server, and you can access it from your phone. You can check to see if there's breaches in any of your windows or doors, or if the lights are on or off, or what the thermostat is set at, and modify these things from your phone. So, the first case that we're going to talk about today is a torque regulated drill and the implementation of it on an assembly line. So, as you can see from the figure, it's a pretty simple design. This is a patent that I pulled off of Google Scholar for one of the first torque regulated drills. And it's basically just a drill bit with a strain gauge at the base that takes in torque data from the output of the drill bit and loads it into a computer. So it's a pretty intuitive, simple design. Um, as a bolt is being depressed into an assembly and tightened, the torque will increase little by little. And then once the target torque is hit, that information is sent into the strain gauge, and that comes out of the strain gauge as a voltage, and the controller knows that the target torque is hit and cuts power to the drill until a worker releases the trigger and pulls the trigger again for the next bolt. So the math is pretty simple, as most of us remember from our mechanics and materials course or dynamics course. Torsion is produced as a product of angular velocity and the moment arm. In this case, the angular velocity is obviously the rate at which the drill bit is spinning, and the moment arm is produced from all the contact points on the fin of the drill bit and the inside of the bolt head. So because there's only one input torque, the reaction, which is being translated into the strain gauge, is going to be equal and opposite of what the input torque coming from the drill bit is. I'm interested in this topic because at a recent co-op, they were discussing the implementation of a line of torque controlled pneumatic drills that would also output torque data for a day's worth of production. The cost for this new system was estimated to be about $36,000, which I thought was pretty incredible, but was valuable to the facility because of the benefits that they would get from having access to this data. One benefit would obviously be the ability to adjust torque up and down for different assemblies, which is something that you wouldn't be able to do with just a regular drill or impact. But also, the torque data would be valuable for removing liability for loose bolts and assemblies that have already shipped out. They would have a report saying that every bolt in the assembly was properly secured. So it would have had to have been something that happened during shipping. And also, you could do defect tracking data you could see, well, is there a defect coming out if the torque is turned up too high that's maybe damaging the assembly or causing paint to crack. And another interesting thing that they could get from this data, other than quality assurance and defect tracking, would also be tracking wear and tear on individual drills. They may have a day of production, and for some reason, one of the drills specifically is outputting a lower torque than it's supposed to into each assembly, and then they can stop the line and replace the drill or figure out what issues are causing the drill to not output the correct amount of torque instead of spending the whole day um, making assemblies, not having the information, not being able to know that the bolts aren't being properly secured to the assembly, which could cause trouble for the customers and other assemblies that the sub-assembly is put into.
Hello everybody. Today we're going to be talking about automated track inspection. Railroad tracks have fairly prescribed inspection periods, which are conducted by field inspectors for the millions of miles of tracks in the U.S. Some tracks require inspections often as twice per week, and this is done physically by people looking at the track directly. Currently, only manual inspection is possible, which is time-consuming and cost-inefficient, and also there are certain areas where it's unsafe for people to go. It's slow, and the inspectors can't be everywhere at once, so issues can crop up rather quickly. Introduction of automated methods could save costs and provide a higher level of safety for the train operators. If automatic systems are connected to the trains themselves, it could check tracks multiple times, and computers can detect certain failures faster than people by running different analyses. Sensors and algorithms. The example system in the source material was a simple handcart modified with cameras to capture images of the track from different angles. It was very simple, and it could potentially be easily modified to go on trains or some other vehicle that travels along the railroads. It took pictures from the side of the track to view the rail itself, and from above to view the various components that form a railroad, like the ties and the railroad spikes. Pictures of the track would then be run through filters to make them discernible to the music algorithm. In particular, these are called Garber filters. It separates the images by lighting into rough white and black images, with the final result being a 1D signal to feed into the music algorithm. This algorithm is used in particular for its ability to track multiple cyclical occurrences. It is also robust with noisy data. In layman's terms, it can track the occurrence of the various parts that make up a railway, such as the ties or the railroad spikes themselves, and it can also track much less oftenly occurring things, like when the tracks come together or diverge, which are called turnouts. Mathematics. The music algorithm uses some rather complicated math to extrapolate the occurrences of the many components that form railroad tracks. Much of it is based on matrix operations to sort through the signal data and determine component periods. The 1D signals are put into the system in the slope-intercept form as we see here, and then it does various processes to get this j omega, which it uses, which is basically its guess for the time period. We can see the final mathematic result here above number 11, where j is calculated. It uses summation with its initial guess, which is L, D being the number of eigenvectors it gets from the decomposed matrix, and it multiplies by AH, which is a subspace, and EJ, which are a representation of those eigenvectors, to narrow down its initial guess to what it thinks its actual occurrence is, to a rather high accuracy rating of 87% for the turnouts and up to 95% for individual components. Applications. Automatic detection systems could be fitted to trains or smaller inspection vehicles. This could speed up inspection time, as rails or vehicles traveling on the rails are a lot faster than people on foot or in a vehicle themselves looking at the rails, and it also could increase frequency of the inspections occurring. Computer-guided systems could detect certain defects with higher proficiency than manual inspectors. The algorithms that they use, depending on which one the system uses, could process data in multiple ways and do various analysis of the signals they get, which could allow them to detect certain things like maybe component rusting or defects in them themselves. It sees more than what the human eye could detect. And then digital reports of track conditions could be used to automatically set up repairs. Whenever the system runs into an anomaly, it could set up an automatic ping to either schedule repairs or to have a manual inspector go and track it themselves, or to investigate further depending on what the system detects. Thank you for your time. I hope you've enjoyed this presentation. I am sorry for my coughing. I am currently a little under the weather.